Anton, I need your help to move to the mixed. I think it's not working. It's like last time. No. Even with that one. Oh, no.
It's weird.
Yeah. Yeah, no, it works. I think it will. Okay, I think it's time to begin with today's lecture. And today we'll be learning more about the data structures. So we started some introduction about the data structure in the previous lecture. And today we'll be learning more what the data structures are and how can we implement our own data structures in Java. And the focus will be mainly on, because this course is not purely something that is into the detailed implementation of data structure. So you will get only like some quick overview of some of the major data structures like linked list and stack and queue. And yeah, so as the name suggests, data structure is something that we can use to organize our data and also to define the operations, what kind of operation that we can perform on the data. And I mean, data is something basic for your program. So whenever you are writing a program, so your program involves some kind of data. And when we talk about the data, we could have a different data of different types. You can have a numeric data, and you can have character type data, alphabetic data, and even the user defined kind of types. So and there could be, I mean, depending on your application, depending on what kind of purpose you are writing the application, there could be, I mean, you might have to need different kinds of data structures. So, for example, you need if it's an application that requires to have only unique kind of data. So maybe you need a data structure that doesn't allow duplicate values. So something like a set. And it could also be like an application that works on more like kind of sorted data, where the data should be organized in some order. Could be like alphabetic order or based on some values or some priorities. So in that case, you need a data structure maybe that supports kind of sorting or on the data. And then depending on your application, there might be like your application requires some specific kind of operations. There are more frequently performed operations. It could be like in your application, the most frequent operation is that you just insert the data. You just keep on adding data, and there is hardly that the delete operations you need, or maybe there is hardly that you need to look up or search for data. But then on the other hand, there could be the applications where you need a frequent lookup operation, that you need to search more frequently than adding or removing. So adding, maybe you've done it only once. You added all the data, and then after that, you keep on looking several times. So then in that case, maybe you need a data structure that supports kind of faster lookup operation that is more designed to support quick and efficient search or lookup operation. So it means like we have a different kinds of needs on our data, and accordingly to support different kinds of needs to organize and to store, retrieve, delete, and look up and organize your data. So we have a number of different kinds of data structures, such as list, arrays, and linked list, queues, stacks. And when it comes to the definition of the data structure, there are like few basic things that you need to define if you want to create your own data structure. For example, sometimes you have an application where you have requirements that cannot be fulfilled by any of the library or the Java API provided data structures. So in that case, maybe you need to define your own kind of data structure that can be used to store and perform different operations on the data. So in that case, the few of the basic things that when you are designing a data structure, you need to decide, at first you need to decide what kind of data it can store, what kind of data you can enter into your data structure. You can enter integer, numeric, float, double. So you need to decide the data type. And then you also need to decide what kind of operations that can be performed. So you need to define the operations on that data structure as well. Can you add, can you remove, can you sort, search? So these are the different, depending on your requirements. So you need to define the data type, then you need also to define the number of different operations that can be performed, and you also need to define some identifier for that data structure. So an identifier is just like a name that you can use to refer in your application to that particular data structure. So it could be like, if you are, and usually the name of the data structure is defined based on its type, what kind of data it is storing, and on its behavior, like if it's like a last in first out, so and then maybe it's like a stack behavior, and if it's like a first in first out, then it's more like a queue behavior. So you can decide meaningful identifier for your data structure. So for example, if you have needs to have a kind of a data structure that you can use to store a string data type, more like a stack, where you that the elements that you added last are retrieved first, then maybe you can define a data structure with the name of string stack. And usually when we need to define a data structure, because as we defined in the beginning, that in the data structure definition, so for example, if you want to define a data structure in Java, you need three things, as we said, that you need the identifier, data type, and the operations. Maybe you don't need the implementation details. So implementation could be done in a different ways, like how do you perform your search or remove operations. So there could be a number of different implementations depending on the way the developer or the users wants to implement it. So, and to define the three basic things in Java, we have an interface definition. So where we can define the data types, and we can also define the number of operations. Okay. So for example, here we have an example of a string stack interface, and in the string stack interface, we define the operations in the form of like abstract methods. So we have just the method definitions and the signatures, and for each of the methods or the operations, we specify what kind of data these operations can handle. So for example, in these operations, we are dealing with the kind of string data. So then we call it string stack interface. So that's just an example. And some of the more frequently used examples of data structures that are provided by the Java, and also similar kind of data structure you have in other programming languages as well. So it's not only just for the Java. So we have like a list, and we already, I think, talked about a list in the previous lecture. So the list is a kind of data structure where you have elements or the data stored in some sequential order. So we have like an index. So like starting from the 0 index until, so every element you add will have some position, okay? And then we have, and in the list you can have a duplicate value, so there is no problem. So in list you can have one data element repeated. For example, if we have a list of students in a class, So there could be same name for maybe 2 or more than 2 students. So that should not be a problem. And in the queue, it's like when your application wants to have a behavior where the data that is inserted first should be processed first. So first in, first out. So for example, like your job applications are for your CPU. So for this kind of scenarios, maybe we need a queue like a first in, first element. And for this queue kind of data structure, so it means like we can insert elements at the end of if there is a new element, the new element will be placed at the end of the existing elements in the queue. But when we remove or when we try to get an element from the queue, we will always get it from the front of the queue. The first element will be true. And then we have a stack, and in the stack we have like a last in, first out. So the element that was inserted last time will be removed or accessed at the first. And then we also have a DQ. It's like a double-ended queue. So the difference between DQ and a simple queue is that in the queue we can add or remove only at one end, either at the front or at the other end. But in the double-ended queue, we can add at both ends. So the new elements can be added either at front or at the left. So it's more like it can give you behavior of both, like a stack and queue. So and then we have a set. So it's more like a list, but it doesn't allow the duplicates. And also in the set, there is no specific position for the element. So we don't have any index for the set elements. And then we have a map. So for example, sometimes you have a data that has a kind of associations in the form of like key value pairs. So it's not like a single element, but you have an element that is connected with another element. So in that case, we can use a map just like a table. And then we have a tree data structures. And the tree is like hierarchical because in the list, queue, and stack, and even the set, they are more like a linear data structure where the elements are stored in some sequence. But in the tree, you have like several, instead of linear order of the elements, you have several levels in a tree. You have a parent, and then you have a child, and the child can have further subchilds, so there are multiple levels. So, and it's, for example, if you want to implement a file system, then you know that in the file system or in the directory system, we have like a parent directory, and in the parent directory you can have a subfolder or subdirectory, and inside subdirectory you can have maybe files or maybe another subdirectory. So you can have a multiple layers. So for this kind of data, it's intuitive to use list, because it's more intuitive to use something like that models tree-like or hierarchical data structures. And then we also have a graph data structures. So the tree and the graph, basically tree is a kind of a form of a graph. In both tree and graph, we store data in the forms of nodes, like an elements. And the difference between the tree and the graph is like in the tree we have something like a root, but here in the graph there is no something like a root or starting point. And also in the tree, between two nodes you only have one path, one connection, but in the graphs you can have a multiple paths or multiple connection between one node and another node. So we will see all of them one by one. So for example, as we talked about the stack, the last in, first out. So everything that you add or remove will be added at the top, at the one end. But if you talk about the queue, the new elements that you add or the in queue, they will be appended at the end, at the last position. But the DQ operation that removes, that you can use to get an element, that will be performed from the first or the front position. And both of these are like sequential because the elements are stored in a sequence. And then we have a DQ and list. And the DQ, as I told you earlier, it's the difference is that you can in the double-ended queue you can add and remove both ends. And then we have a list. And the difference between the list and the queue and stack is in the queue and stack we can only access or add elements at specific ends, either at the front or at the bottom. We cannot add or get elements from the middle or any specific location. However, in the list, we can get or add element whatever location we want. We can add at the front, we can add at the second position, third position, or we can remove from the middle, whatever position arbitrarily we can decide, and we can add elements from the list. So that's the fundamental difference between list and the other one. And then, as we said, that in order to define a data structure, you need we usually use interface definition. Of course, you can do it without defining an interface. You can directly implement a class that implements a data structure, but then maybe it's reusability of that class, and you can will not be as supportable as in case of interface, because then you can share your interface with multiple clients, and they can use it, and they don't need to know the inner level implementation detail. They just only need to know what input values and what output values and what are the operations that need to be performed using that data structures. Okay, and another important thing is, I mean, when it comes to the data type, when deciding a data type, yeah, we can have like 3 different options. We can use either a fixed data type for a data structure, like integer or float or double, or we can use object type, which is the parent class for all the classes in Java, or all the types in Java. And then we can also use a generic type. And we know that from the lecture on the generics, Java generics, if you use a fixed type, then that data structure can be used for only that kind of data. You cannot use it for any other data type. But if you use it, if you decide that when you are designing your data structure, if you choose the data type to be an object, of course, by using object, you can store any kind of classes that are subclasses of the object. So you can use strings, you can use integers, float, doubles, and any other user-defined data type like student, teachers, this kind of data you can store in that. But the problem with the object that we learned in the Java generics lecture was that then you need to explicitly typecast. Every time you access data from a data structure which is implementing an object, using an object. So if you have, you can store in a data structure of type object, you can add student data, you can also add a teacher data, you can also add a data about maybe books, any kind of thing that is a subclass of object data type. But then when you are trying to retrieve, when you are getting the data back, you need to remember what kind of data, what is the type of that data, and you have to explicit typecast it. So for example, if you are trying to retrieve a student kind of object and type of data, then you have to typecast into the student type. If you are trying to retrieve a student and are casting to something else like a teacher or books, then maybe you can have like a class cast exceptions. So, and that's the problem with the use of. So it's more recommended that you use Java generics, because then on the Java, if you have defined a data structure using generics, then at the runtime you can specify for what type of data you want to use this data structure, and by specifying at the runtime or when you are creating the instance of that data structure, you will specify the type, and then compiler will make sure that you are adding right kind of data and accessing right kind of data from that data structure. Is it okay? Okay, so, and when it comes to implementation of these different kind of data structures, so these are more like, the different names and behaviors. So how internally the data will be stored, because we are not talking about data structure. It means like we will have a multiple data. We will not have only one kind of data. We will one instance of data. We will have multiple instances of a data. So for example, we can have a data about 100 students. So if you are running an experiment, and that experiment involves data collection from maybe 2,000 different people. So then you have data from these 2,000 people from maybe 5 different cities. So internally, we know that when we have a multiple data, we use arrays instead of simple variables. Okay. So one option is that you can implement your data using the arrays. Okay. And the other option is that you can use maybe some of the Java API classes like ArrayList. And then that we will see that we will have another option, like we can create a linked list, and we will see that what the linked list is. The problem, and then of course each of these different choices, they have their own pros and cons. So for example, if you decide to use array type, we know that we can have a problem with the size, because when you create if you use an array to store a data, you need to specify the size. Okay, and then if that array becomes full, then you need to create a new array. So that's like an extra something. And also another option is that you can use an array list. Okay, but we will see that we also have a problem with the array list. For example, if you are using an array list, and you are implementing a list kind of data structure where you can add elements at any position, and you have already added 10 elements in that data structure, but if you want to add a new element in the middle, then you have to shift all the elements that was already added on that position. Okay, so for example, maybe it will be easier if I show it using mixed whiteboard. Will it work? Oh.
It's a problem since it doesn't exist as a layer.
Okay, but I think, I mean, that's of course you guys in the class can see it on the whiteboard, but the problem will be for the distant students. So no. Is not possible from here.
Unfortunately, there is no layer. Otherwise, I could just click
Okay.
the same as we did before.
Mm-hmm.
But I might be able to move it or shift it with this, but I don't know how it is to reset it. But I think it would be fine. Question is. Nope. Doesn't seem to work. Should I go and check?
No, I think I can explain it with that. For the distance guys, we try to switch to the whiteboard mode, but unfortunately we did not succeed due to the problem with the system we have over here. But I mean, it's simple. Like if you have if you're using an array list to store some values, and for example you have already you can visualize this like if you have 5 people sitting on 5 chairs in a row, and then if you want to insert somebody, if there is a new guy comes in and he wants to be seated on the position number 2, then you have to move the person who is already sitting over there to create a space. And it's same like if you remove somebody from the middle, and then you have to ask the guy who was sitting next to him to come back to take this position. So that's the so it means like for such kind of operations, the array list is not a good choice. Okay, we will see that these kind of operations can be very efficiently handled by using linked list data structure. Okay, so it means that the choice of implementation techniques can affect the performance and the memory, because if you are, for example, the problem with the array is like if you have defined an array of size thousands, just to make sure that you will not have a problem with the insufficient size. In that case, for example, you create an array with the size 1000 or maybe 2000, but in the application, maybe the user has only 100 elements. In that case, there will be all the other indexes or the spaces will be just wastage of memory. Okay. So to give you an example of how we can use arrays, or how we can use linked list or array list to implement a simple list data structure of type integer. Here we have an example interface or example where we have defined simple operations: add, remove, get, and add. So the add operation simply inserts a new element, new integer value in a list. Add at, if you want to, instead of the add at will, the simple add will add the element at the end. But if you want to add at specific position, maybe at the front or in the middle, then we have a add at, where you can specify the position or the index value. And in the by the get, you can see that if you want to access some element at some specific position, then you can use this method. So we have already, some classes that are implementing this kind of. So we have an integer list interface over here, and then I have a array int list class which is implementing this interface. And in this implementation, in this data structure implementation for the integer list, I'm using a simple array of integer values just to store the values that we add. Okay. However, if you see in the add method, we just get a value, integer n, and we store it inside. And every time when we store it, a new value, we increment our size, because initially the size will be 0, and the size shows the number of current elements in that list. So for example, initially there will be no elements, but if you add 1, 2, every time the size will be get incremented. And because now we are using an array based implementation, and we know that after some time the array becomes full. And if the array becomes full, every time when we add a new element, we check, after adding we check that if it becomes closer, if it becomes to the maximum limit, then we resize it. And the resize means like we create a new array and shift the values from the older array to the new array. Okay. But then if you want to add a new element at some specific position, at first we need to check the index. It could be that the user specifies an invalid index, like -1 or -2. So, and also it could be like user is specifying an index which is outside the maximum limit. So we check index, and in the check index, it's like a private method where we check the index, and if the index is not within the limits, then we throw an exception, like index out of bound exception. Other than that, if we go back to the add at method, so if you want to add an element, let's say at some specific position, then we also need to shift right the elements, okay, from that position until. So for example, if you want to add a new element at this position, let's say if for example, I have a class over here, list main, yeah. So And in this list main, we have inside the main method, I just created a new object of that type, array_int_list, and on that object I call this method test list al, and I pass the object of type array list. And in this method test list, if you see over here, I just added some values, and then I try to print that list. And after that, we can use the get method and the different methods to get the values. So for example, if we run this program over here now, okay, so I have added these values, okay, and in this value means that I have added these 10 different values, and the size is 10 at position 5 is equal, now the value is 50. But if I want to add a new value at position 5, I can do that using the add@ method. So let's say after this, I say like list.add@, and now I specify the index 5, and sorry, no, here first comes the value, and let's say 200, and then I say index 5, okay, and after that I just call this method again and maybe print again. So now see, yes, at position 5, before the element was 50, but then when I added a new element 200, and if you see here after the 40 the value was 50, but now 50 has been moved one position towards right. That's what I was trying to say, like the drawback. Every time you add a new element, you have to move the elements to the right one position so that you can have a space or you can have a room for a new element to be added over there. And similarly, every time you remove some element from the list, you have to shift towards left so that there is no empty or something like non-existent value in your list. So this is just a simple explanation of the different methods. The resize is like if the array size becomes full, we just create a new array, and the length of the new array will be the 2 times of the existing length of the existing array, okay. And in the remove, the same like, so for example, if we decided to remove an element at position 3, okay, so it means that from that position, all the elements that are, so we started a loop starting from that element, I is equal to index until the length, until the size, and then we shift the values I plus 1 towards that was to the right of the element that we want to remove, and we assign it back to the element that we want to remove. Do you got this thing? I can explain it more easily to you guys, but the problem is it will be not visible for the students on distance. So for example, if you have a list where you have added these values 10, 15, 20, 25, 40, and then you call, so the first index is 0, 1, 2, 3, 4, okay, these are like indexes. And if this the name of this is like list, and if you call list dot remove and you specify the index like 2, so it means that this 20 you want to remove this 20. So after removing this 20, what should be the behavior of your list? Should there be like 0 value or null value or something? What should be there? It means like you have to move, after removing this, you have to move all the elements that are on the right side to one position to the left. for example, if you have a really large list where you have like thousands of elements or 500 elements, and if you have removed the element from the front, then you have to move all those different elements to one position. And the same goes if you want to add a new element over here. Then you have to create a, for example, instead of removing, if you decide to add list dot add at, and then you specify the value like maybe 200, and the index is 2. In that case, if you want to add a new value instead of 20, you want to add at this position a new element, then you have to move this element one step towards, and then so that you can add a new element over this position. And then it's also important that when you are, if you're trying to implement a new data structure, then you also need to, along with providing operations or methods that can be used to add and remove elements from the data structure, there must be some kind of operation that can be used to visit the elements, to iterate, okay, like a for loop. By using a for loop, you can see the different elements in your array. So similarly, in the data structure, in the Java provides us with this iterable interface, and that returns us with an iterator, an object of type iterator with the iterator method. And we can use this iterator object to visit different elements in a collection or in a data structure using the next and has next methods. Okay, so and if you want to have your data structure to this kind of functionality, then it means that your data structure should be implementing this interface. So for example, if we see over here, when we define this integer list interface, we make it a type of iterable. We extend it because this is an interface. Okay, so we cannot implement an interface cannot implement another interface. So the only thing is that you can extend it to some other interface. But when we define a class which implements this interface, so for example, we have this array int list, then we implement, which is implementing this int list. So it means that there must be some method called iterator that comes from this iterable interface. And this iterator method returns us iterator type object of type iterator. And if you look at this method, it is returning a new list iterator, an object of type list iterator, which is an inner class over here, class list iterator, which implements iterator. And in this case, you can see that we have implemented our next and has next methods. Okay, the has next method simply checks that whether there are more elements in the list or not. Okay, so you start from the 0, and every time you visit an element, you keep on incrementing the count, and until the count is less than the values, then the total elements or the size, then you keep on visiting or returning true value. So it means that it is also important that when you are implementing or designing your own data structure, so you should provide a support for iterable interface, or that user can use to visit the elements. And we can use, using this iterable interface, there are two ways to visit the elements. The one way is using this has next, using a while loop, and then until there are new elements in this in your data structure, it should keep on returning true, and it means that your loop will keep on visiting the elements. And the other way is that using for each loop, and using the for each loop, which basically, the syntactic sugar for this has next and the iterable interface. Okay, and this is just simple the code from that class that I just showed you. And then we have this linked list implementation. I don't know how much time we have now. Okay, I think we can finish with this linked list. think before, or maybe not. In the linked list, as its name suggests, that it's a list of elements which are connected, which are linked with each other. So basically, in the linked list, instead of using array, we define our own object that can encapsulate a value, and then the first element that we add, the list only knows the first element in our list. All the next elements, it's like a chain, you know, when you have a silver chain where you have a one node, single element or node, and then you connect it together with the next one. So every element in the list has a pointer to the next element in the list. Okay, so it means that to define a linked list, we need two things. We need to define the list, the size for the list, that will be automatically counted based on the number of the elements, and then we need a node type. And I already, explained you the reasons why we need a linked list instead of array list or array simple, because the problem is with the remove and add at methods, because then you have to shift the elements if you're using it. So the linked list is usually made of two classes, list and node. So it means that if you want to have a linked list based implementation, then you need you need to define two classes. One class that maintains the overall representation for your list, and other class that implements the individual nodes in the individual data elements in your linked list. The first time when you create a linked list, so if you try to define a new linked list, to define a new list, you basically need two attributes. You need a head, and we will have an attribute for size. Initially, if it's an empty list, size will be 0 and head will be pointing to null, because there is no element, there is no node in that list. But whenever you try to add a new data or a new data element in the list, you will create an object of type node, like using a new node. If you have a new, because we said that to implement a linked list, we need two classes. We need a class that represents the overall list, and then we need a class that implements individual elements in that list, and that class we call it a node class. Okay, and in this node class, so if it's a node class, we have two attributes again. The one attribute we have is a value, like a data value, and the other attribute is next. And when you add this new node into your list, this head, you will pass the reference or the address of this new node to your head, so that you should establish a connection between the list and the new node. And whatever the value you want to insert will be stored in this value attribute. So let's say we want to store a value 10, and this next will be pointing to null. And then if you decide to add a new element, so you add a new node You create a new node and you pass the value of that you want to insert, let's say 20, and then so similarly we moved this head to here, and now we want to link this, so this next will now point you to that node, and here we will have a null value. So that's what I try to represent over here. So, and every time you add a new element, you also increment the size variable. Initially the size was 0. When we added the first element, we do it size plus plus. So every time you add a new element, the size will also be incremented. So here we have a linked based implementation. Okay, so we have a class with the name of linked int list, which is implementing the same interface with the name of int list. However, instead of using an integer array of values, int type array, we are now using a node class, okay, and the size is initially equal to 0. And when we add the first element, we check if the head is equal to null. It means like if it's like an empty list, then this new node should be assigned to the head value. The head should, the address of this should be given to this head pointer in the list. Otherwise, if it's not an empty list, then we need to move from the starting until the last node in the list. And on the last node, once you have found the last node, you can create a new node and set the address of this to the next pointer of the last node. So you will get the copy of this code with the lecture, and then you can see how does this we have this linked int list implementation, which is implementing the same methods as we have done in our array based implementation. However, you can see that if I can show you over here, both this array int list and this linked int list both are implementing the same interface int list. However, one is using a primitive type array, integer type array values to store the data elements. In the other, we are using node type, which is our own class, to store the values and connecting it using the linked list based mechanism. And if you go to this node class, which is like an integer, an inner class defined in the same class, you can see that public class node. And in this node class, as I told you, that we simply need two attributes. One attribute with the name of value to store the actual value, and the other is the next pointer. And that the pointer of that type is also a node, because we want to point to another node. And then we have just a simple constructor method which takes the values and assigns that values to this field values. And there is nothing complicated over there. And similarly, we have the get and index of methods, and the get method internally it behaves similar to the array based implementation. Before checking an element or returning an element, it checks whether the index is a valid index or not, and if it's not a valid index, then it throws a index out of bound exception. However, the important thing is to see over here now. Now we have a add at method. Let's see, we have a list, this initial list of size 4, 1, 2, 3, 4. And index of this will be again 0. This will be 1, 2, and 3. If we decide to add a new element, so at index over here, at index 1, what can we do? So simple is, so if we have like, this is the index 0 and this is 1, if we decide to add a new node at index 1, I don't need to move this one friend. I simply need to replace the pointer and direct this to point this. And similarly, if you want to remove it, you just need to remove this pointer and set it back to the previous element. Okay? So, for example, I want to add a new element with the value new in between these two nodes. What I need to do is, I need to find the element before the index where we want to add a new element. And once you have found the before element, and in that before element, then you can take its next and assign the new node to this next. Okay? So, in the add at, we check if the index position is equal to 0. If you want to add at the first, it could be that the user decides to add at the beginning of the list. In that case, you need to assign the new element to the head. Okay? Head will become the new. Otherwise, you have to go to the element where you want to add using a loop for integer I is equal to 0, starting from the 0 index until the position where you want to add a new element. And once you have found this before element, then at first, and this is also, the order is very important, because before assigning this new element, you need to where is the address of this element? The address of this element will be stored over here. So, you need to store this address of this into the next element of this. So, for example, the name of this is like a new nw. So, you have to call nw.next is equal to, and the node name of this is like, for example, in this case is like before.next. Otherwise, you will lose that value. Okay? And then you can set it back. And the same goes if you want to remove it now. And in this case, you see that when you added a new element, you have not moved any of the elements to the further position. It was just simply a passing of address from one variable to another variable. And similarly, if you decided to remove it, before this next was pointing to this node, but now we called the remove operation and we want to remove this element, remove index 1. So, what we need to do is simply to point this next from here to here. And how can we do that? Again, we need to check the index first, if it's a valid index or not. And then if somebody wants to remove the element at the first position, in that case you simply need to switch head from first element to the second element. Okay? Otherwise, you need to find the before element and then the same thing, move the pointer of the before element by skipping one element in the sequence. The implementation of the iterable interface, again, it doesn't matter if you are using array-based implementation or if you are using linked list-based implementation. It's always good to have a iterable interface, and the method for that is the same. For the iteration is the same. You will use node.next to visit one element, and then you keep on visiting all the elements that are connected together. So now we have seen a simple version of a linked list. where we have only two things. We have the head, and then we have a size and the node implementation. In the simple form, the list only knows its head position. You only need to know the starting element, and from that starting element, you can visit all the nodes until end, because every node knows the next element in the list. However, a problem with this kind of list is, of course, the add at and remove method has simplified the operation in the life, because in the array-based implementation you have to move the elements. But the problem is still, if you are adding a new element at the end, for example, towards the tail side, then before adding you have to visit all the elements from the head until you go to the head or the last element. So what if we have a new field in the list, tail, where alongside with the head we also always keep track of the last element. So that's another smarter version of the linked list implementation that we call head and tail based implementation. Okay, and in the head and tail, along with the head, we have a new field with the name of tail. And the first time when you create a new list, both head and tail will be pointing to the null. And every time you add a new element, for example, when you added a new element, the head will be pointing to the new element, and the tail will be pointing to that also, because it's only one element. So the head and tail will be pointing to the same node. But if you added a second element, in that case, head will be pointing to the first, but the tail will be pointing to the second, and 3, 4. So in this case, we have a tail pointing to the last. So in that case, so for example, if you decided to add a new element over here, between here, then you don't need to start from maybe, or if you want to add or remove a new element at the end, then you don't need to go from this way. You can simply use the tail pointer to remove or add elements at the end. Okay. We also have a double linked list, and in the double linked list, in the simple linked list, we only have a pointer towards forward direction. We can only visit or traverse the list in one direction, but we cannot move to the backward direction, because we only have a pointer which is pointing to the next element. In the double, you have another pointer in the node which is called previous. That point, the next points to the next element, and the previous points to the element which is before him. Okay. So in the node, we have a next which is pointing to the next element, and we have a previous pointer which is pointing to the previous. In case of the first element, this will be null, previous will be null, and in case of the last element, next will be null, because there is no element next to it. So these are like two simple, more advanced implementation of the linked list. And the advantage of using this way, double linked list, is that then you can visit the list in both directions. You can move backward and forward as well. So for example, if you have to visit a list in a reverse order, then maybe this double linked list array will be more efficient than a simple linked list implementation. And then just to give you a more summary of what are the advantages and disadvantages of linked versus array-based implementation. As we know that if you use the linked-based implementation, we don't need to remove or shuffle the elements in case of remove and add. We don't need the resize mechanism, because there is no size, there is no array involved. So you don't need to have a resize functionality if you're using a linked list. So as you create a new object, and that you just need to link that new object. And there will be no wastage of memory, because you don't need to specify the size from the beginning. However, one of the problems with the linked list based implementation is in the array-based implementation, the get operation is quite fast. You just specify the index and you retrieve the element. However, in even whatever kind of implementation you use, either you use a double linked list or you use a simple linked list, you have to visit quite few elements to get to the specific element. So for example, if you're using a simple linked list, and if the get wants to access the element at the end, then you have to traverse all the elements. And even if you are using double linked list, and if in case of access for the element in the middle, whether you start from the front or you start from the bottom, you have to traverse all the elements, at least half of the elements, to get the element in the middle. And then there's just some, I mean, you don't need to implement all these things. Java I have already provided you with, even with the linked list based implementation with the name of java.util.linkedList class, and that linked list Java API class, it implements double linked list. And we already have seen array list, which is an array based, and the vector class, which is again array based, but it's more thread safe or synchronized. Okay, I think let's take a break for 10 minutes, and after the break, we continue with the tree data structures. Can you put the 10 minutes timer?
Yeah. Quick question.
Yep.
I tried to implement this queue.
Anton. I think the time is over, but it's still. It has started the countdown again. I don't know why. Okay. Okay. Next, we have a tree data structure, and as we said that in a tree, instead of it's basically a set of nodes as well, similar to kind of a linked list that we have a nodes, and that the nodes encapsulate or wrap the values that you have. However, in the linked list, you have like more in a sequential order, but or in a linear kind of data structure. But this tree and the graph, they are more like a hierarchical data structure, where you have multiple layers or the levels, and so there is some basic concept in a tree. The node that doesn't have any parent, we call it like a root node or a parent. Of course, I mean, you can have parent nodes other than the root. The root is only that doesn't have any parent, and then you have a child nodes, and the nodes that doesn't have any child. I mean, one node can have more than one child, but not more than one parents. Okay, and the nodes at the bottom that doesn't have any child nodes, we simply call them a leaf node, similar to the tree analogy. And also, an important thing is that in a tree data structure, between every two nodes, there will be only one connection or only one path, that we call them an edges. Okay, in terms of tree terminologies. And if there are like more than one paths, then it's not a tree. Then it's more like a graph. So it's some theoretical concepts, some terminology about the tree. So, and that's, for example, what is a path and what is like a length and height. So for example, the path is like if you have, let's say, if we go back here. The path is simply, I mean, if you want to find a path from node A to K, it's all the nodes from the node A to reach this node. So, for example, you start from the node A, B, E, and K. So these different connections are the edges. They define a path. And if we say that n is the parent, n1 is the parent of n2, which is the parent of n3, and so on, and then the path of the tree and the length of that tree will be, the number of nodes minus 1. So basically, you count the number of edges to get the length of that path. And then we have also ancestors and descendants, like the forefathers and like the grandparents and the grandchildren. And the height of the tree is the length of the longest path. So if you need to define the overall, I mean, we have a length of the path, and then we also have a length of a overall tree, and the height of the overall tree. The height of the overall tree is the longest path. Okay, and then we also have a height of a node, and if you want to check, and depth of the node. The height of the node is the height of the longest path from the leaf nodes until that node, and the depth is other way around if you start from the root node. So it will be easier to see with the example. So for example, here we have a tree. In this case, A is the root node, okay, and then all these nodes like K, F, L, M, H that don't have any children, they are like a leaf nodes. And the height of the tree is like the longest path, height of the longest path. So, for example, yeah, I mean, if you choose any of these two or any of these, so they have a similar height that is equal to 3. Okay, the number of nodes on that path minus 1. And if you want to check the height of a specific node, for example, height of a node B, so you have to start from the leaves, the longest path, and you have to count on the number of edges. So in this case, the height, because the longest path is from K with the leaf node, and the number of edges are 2. And if you want to see the simply the depth or the level for that node, then you have to start from the root node. And in that case, there is only one edge from root until B, so its depth or level will be 1. And these are like just some example scenarios where you need, for what kind of data we can use tree data structure to model. So, for example, as I said in the beginning, if you want to represent your file system, then you can use, or even maybe if you are if you want to design a parser tree for a compiler, where you have a statements, and inside the statements you can have nested statements and the blocks. So basically kind of data where you have a hierarchical relationships, where you have one starting point and then you have several branches, and then on that each branch you can have sub branches. And then so far we have seen a general tree, and in the general tree, I mean, one node can have more than one. It can have one child, or maybe 2, 3, 4, there is no limit. But we have a special case, which is like a binary tree or a binary search tree. And the definition of binary search tree is a tree where a node cannot have more than 2 children. Okay, so like a binary, so you can have either maybe 1 or 2 or not more than 2. Okay, and then we have a special case of a binary tree, okay, which we call a binary search tree. And the rule for the binary search tree is that for every node, all the values that are lower than the value on that node will be assigned to the left on the left side, in the left subtree, and the values which are greater than the node itself, they will be assigned on the right side of that node. Okay. So simply a binary tree with the following properties: for each node x, the values of all nodes in x left subtree are less than the value of x. Okay. So for example, if we say that, let's see, I hope it will work.
Press the yellow number 2 first. No,
Okay, so now we found a fix for this whiteboard mode. So for the binary search tree, as we said that so let's say you have these values like 20, 10, 14, 15, and 30. Okay. So let's say we start with the first value. So there is no node in the tree. So, and then we take the next value and we check it. If it's less than the current node, then it should go to the left side. We go again, we take this value 14, we start from the root node, compare it with the current value. 14 is less than 20, it should go to the left side, and we come here, we compare with this value. 14 is less than, no, 14 is greater than 10, so it should go to the right side, and we add it over here. Then we go again with the 15. Start here, less, go here, 10, come here, 14, and 15 is again greater, so we add it to the right side. We take 30, compare here, it's greater, so we add it. Okay, so that's the simple philosophy for the binary search tree. So all the values which are, yeah, thank you. Yep, perfect. And we usually, for the binary search tree, we assume that we don't allow the duplicate values. Okay, so if the value is already added. However, in case if you want to allow the duplicates in your binary search tree implementation, then you, for the duplicate values, it means that that value is already existing. So for example, we have already added 10, and if you want to add another instance of 10, then you can decide either you can add it on the left or on the right side, because it's not rather less or greater, it's the same value. But then you should be consistent in your choice. If you are adding the same values to the left, then it should always be on the left, or if you decided to add on the right, then it should always be on the right side. And here we have the two different trees. The one is the simple binary tree, another one is the binary search tree. What is the difference? The difference is here, if you see this value 6, it's lower than the 7. So it must be on the left side. If it's not on the left side, then it's not a binary search tree. Then it's maybe a simple binary tree. So to make it, and it's also very important for a same tree, if you have a same number of values, but if you add them in a different order, then you will get a different tree. You will not get a same tree. I don't know if we have some example over here or not. Yeah. So in this case, for example, the values are same, 22, 19, 41. So you will see all these values over here as well. But in this tree, we added it in a different order. We started from the 22, and then we added 19 and 41. But in the other case, we had started from the 37. So we get a different tree. Now we have seen the basic terminology, that what is a tree data structure, what are the things involved. So we have a root node, and we have a left subtree, we have a right subtree, and then we can have binary search trees where we have a special rules. But now the question is, if we have to implement this thing. So for example, if we want to define our own binary search tree, yeah, so how we can do that in Java, in terms of Java? The simple thing is, if it's a binary search tree, I've created an example class with the name of integer binary search tree, and similar to the linked list, where we have a class that is representing or modeling the overall linked list, and then we have a node class which is implementing individual nodes. Same is here. We have an overall implementation class into BST, and then we have a private BST class which is representing the internal nodes in our tree, or the binary search tree. And if we look at in this class binary search tree, we have basically 3 attributes. We have the value for each node, and then we have the left and right for the left subtree and the right subtree. Initially, when you create, when you add a first element in your binary search tree, both left and right will be null, pointing to the null. But so every time when you add a new element, so you take a value and you pass it to the value field as an input parameter when you create a new object. And then we also have this add method, so maybe it will be more easy to understand if we open it over here. Okay. We have this integer binary search tree, and in that we have only one attribute, one field of type binary search tree node private inner class, which is an inner class, and in that class we can see that we have these value and then the left and right. When we add the first element, we check that if the root is equal to null, it means that there is no existing element in our tree. So in that case, I just simply create a new node using this BST and set it to the root attribute. Otherwise, if the root is not equal to null, it means that there already exists some element. In that case, I have an else part, and in the else part, I call the add method on the root node. So it means that we have an add method in the binary search tree as well. So for example here, and in that method, I take the value and I compare that value with the existing value. If it is left, I recursively call it on the left part, and if it is greater, then I recursively call the add method on the right part. So see, if n is less than value, okay, it means that I should go to the left side, and in the left side I check if the left is, it could be that the left side is empty. If it's empty, then I just assign it on the left side. Otherwise, I recursively call on that node which is already over on the left side, so that I can go to the bottom, the lowest node on the left side, and same is on the right side, for the right side. So here we have two examples, okay, and as I said earlier, depending on the order in which you, even if you have a same data, but if you added that data in a different order, then you get a different trees, binary search trees. And also, yeah, can you spot the problem in the first book? Now you have already seen it, and I also already have seen it. So now the fun is already gone. So the problem is here, this is not in the right position. So because 16 is less than, so it should be yeah, over here. And also we don't allow duplicate entries. But if we try to find what is the advantage of using this binary search tree, can you guess over here right now? Why we are making sure that this less value should be on the left side and greater value should be on the right side? What can we achieve with this thing? Faster to find the objects.
Instead of searching the whole tree, you have some kind of...
Exactly, yes. So we have kind of organized data. We have data which is kind of sorted. We have already organized data. So every time if you are looking for a value, you start from the root node and you compare it, and then you, if it's a smaller, you ignore the 1/2, and then you go to the next level, and on that level you check again, and in either case, if either it will be less or greater, or it will be that element which you are looking for. If it's not less, if not greater, then it's the element itself. Okay, so this allows us faster search operations, and we use, it means that you should use tree data structure for applications that require the data to be organized in some particular order, and where you want to have a faster lookup operations. So it means that the complexity of the lookup operation or the search operations is log 2 of n, the number of the elements and then you take the because for example, if we yeah, if we want to find 14 in this tree, so we start from here. Instead of we see 14 is less, we come to this node. We make another check. It's still less. We come here. Another check. We come here. Another check, and we find the value. So we only performed. We have like 9 nodes, but we have found, instead of visiting all the 9 nodes, we have found the element that we want in just 4 steps. And the same is if you want to find an element that does not exist. Okay, you can find it in a steps, in a number of steps, which is equal to log 2 base log 2 and the value of n, and the n here is the number of the nodes in your whole tree. However, sometimes, depending on the elements and the order in which you add the elements, you might have time complexity which is O log n, even if you are using a balanced search tree. So for example, here we have an example. In this case, if I want to find the element 4, I have to visit all, starting from the 1, 2, 3, 4. In the worst case, it means the complexity will be, instead of log n, it will be simple n number of times I have to visit it. The solution for this kind of is, because this is, if you see, this tree is just growing on one side. Okay, so the solution for this kind of problem is that instead of having unbalanced, because this tree is not a balanced tree, it has all the elements on the right side, and for such trees we call them unbalanced trees. And the solution for this tree is that then you can have some kind of a self-balancing mechanism in your, that doesn't matter the order in which you add them, your tree should reorganize itself to make sure that it doesn't grow on one side. So we have a self-balancing by such trees is one that automatically attempts to achieve a balance. And the definition for a balanced tree is, the difference between your left and right, height of the left and right subtree should not exceed more than 1. So for example, here, in this case, if we take the 5 as a node and see 1, 2, and from the right side 1, 2, that's fine. But if we talk about this one, it's 1 and the other one is 0. But it's still the difference between the two is only 1. So it's okay. It's a balanced tree, but not maybe a perfectly balanced tree. The perfectly balanced tree is one where you have no real difference between the left and right subtrees. And another formulation is that a tree is perfectly balanced with the depth n contains 2n plus 1 minus 1 elements. So for example, here we have the depth of this tree is 2, and if we apply the n, which is the depth over here, so n plus 1, 2 raised to power 3, which is 8, and 8 minus 1, so the number of elements are 7. Okay, so if you have exactly the same number of elements in your binary search tree, then it's a perfectly balanced search tree. Otherwise, it will not be a perfectly balanced. Yeah, and why you need a perfectly balanced search tree? Because it helps you to have faster search operations. Otherwise, you will be only having a tree which is inclined in just one side, and then you have to visit more elements. And then, as we have, traversal operations for other data structures like for the linked list, where you have iterators to visit the different elements. So for the tree data structures, we also have mechanism to visit the elements in the tree or the nodes in the tree. And basically, we have three different strategies. We have in order, we have a pre-order, and then we have a post-order. And on top of that, we have like depth first and breadth first. Okay. In the depth first is when you visit more towards downside, towards more like a vertical, starting from the root node, and then you go to the deeper level. And breadth first, as the name says, when you visit, is more like on a horizontal level, and then you complete visiting nodes on one level, and then you go on to the next level. However, in the depth first, we have, as you can see, that we have three main cases over there. In the pre-order, we first visit the node itself, and then we visit its left subtree or the left child, and then we go to the right. We will see how we do that. And in the in order, when you visit the node itself in the middle, it's like an in between. You first visit the left, then you visit in the middle the node itself, and then you go to its right side. And the post order is when you visit the node after visiting its left and right subtrees. So, for example, here, if we say we have this binary search tree, and if we apply the pre-order means we visit the node first, starting from the root. We visit the root node 4 first, then we visit the left, and we go the left side, and on this left side we visit the node itself first. So we will visit 2, and then we go to the left and visit the node, but there is no left, there is no right. So we go back, and after visiting the node, since the order is like in the pre-order, you always visit the node itself first, then you visit the left, and after visiting the left, you go to the right part. On the other hand, if you are visiting the in order, you visit the left first, then the node itself, and after visiting the node, you go to the right side. We start from the root node, and we go to the left first, 2. However, we don't really, print its value or access its value, because we need to visit first the left side. So we go to the 1, and then we continue all the way. Sorry. But if you look at over here, the output, it means that if you visit the binary search tree in using the in order traversal mechanism, then you get the values in ascending order already over there. So you don't need to have any sorting on those values. And in the post order, as the name suggests, that you visit first the left and the right, both of the subtrees, and after that are the child nodes, then you visit the node itself. So in this case, we're starting from the 4 node itself. We go to the left first, and from here we go to its left first, and then 1, 3, and after we have visited both left and right, then we visit the node. And the same goes over here. We cannot print its value because its right side is still left to be visited. So we go from the 4 to 6, and from 6 to 5, and we print it 5, but we don't print 9 because the 9 has a 8 part over there, and then we go back. And then we have this breadth first. All the 3 that we have seen before, like in order, post order, and pre-order, they were depth first tree traversal strategies. Okay, we were going downside. Okay, and in the breadth, first we take a level and visit all the nodes on that level. So for starting from the 4, visit 4, there is no more because it's a root node. Then we go to the level, next level, and visit 2 and 6, and there is no more. Then we go on the next level, and in that way we keep on visiting until there is no more left. Okay, so this brings us to the end of today's lecture. I will upload, as usually, all the example code and presentations to the Moodle page. And I have, just for your information, if you have not already noticed, I have uploaded 2 example exams on the Moodle page, just to give you an idea what kind of questions there will be in the final written exams. And in the coming week, we will continue with the graph data structures, which is kind of like a more complicated form of tree data structures. Okay, so before closing the session, if you have any questions, of course. Otherwise, goodbye for today, and we see you next week.